And usually we have a volunteer for switch off the camera. Not Verdiana, because Verdiana is the volunteer of last two lectures. So, who is the volunteer for today? Or Andrea, or Sebastian? I've decided.
Nobody wants to.
I can do that, but you can give me 15 minutes.
Okay. No, okay, don't worry, but it's better because not for Valentina and Alessia, but it's for about for me. They are known. Okay, I think that I can leave the floor to Mario.
Okay, thank you, Valentina. Please let me share the screen. Okay, I will directly share the PowerPoint. Okay, can you see my screen now? You should see the PowerPoint.
Yes, sir.
Yeah, okay. Perfect. So, as Valentina said, I am Mario Caterino, a mechanical engineer, and I am original from the University of Campania, Luigi Vanvitelli, Unicamp. I am here to introduce the course that will be led by Valentina and me in operations and maintenance management in smart manufacturing systems. As Professor Di Pasquale said, sorry, okay, let me share the screen in full. Okay, can you see the full screen now?
Yes.
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 Perfect. So, as Professor Di Pasquale said, I will lead the part related to smart maintenance management of production systems. So, we will focus only on maintenance, and in particular on the last maintenance topics that have been achieved in last years, because, as you know, Industry 4.0 technologies are changing the world, and also an important part of all industrial plants as maintenance is still adapting to these new technologies and concepts. So we will start from the beginning of maintenance systems, so from the base of maintenance, with introduction also some definitions, some part of reliability theory, and then we will arrive to the latest innovative maintenance systems developed in the industrial plants. Now, I think Professor Di Pasquale already said to you that this is a first year course. So we don't have a very specific, for example, books that I can give you. I suggest to carefully follow the lectures and take notes on the slides and on what I will say. I can suggest this book from which I will take some parts that will on which we will speak in future, and every time I will take some references from a journal, I will put into the slides so you can directly have the references. Now, the program of the course is the following. Today we will just recall some fundamental maintenance concepts. I hope this will be for today, and maybe also for the next week. We will give some definitions to introduce you about maintenance, even if I think some of you already know something about maintenance. Then we will introduce three fault analysis techniques. We will talk about fault analysis techniques such as the FMEA or FMECA, that are the first one, failure modes and analysis, which is useful to provide qualitative information about the failure modes of machines. And it is similar to the FMECA, but this last one also consider a criticality analysis, and so it is considered to give information, quantitative information about the failure modes of machine. We also will see something about the fault tree analysis, that is another technique for failure analysis. Then we will have a lecture. We will focus on the typical classic maintenance policies, introducing the most important concepts on them. And the second part of the course will be entirely dedicated to the innovation brought by the fourth industrial revolution in the maintenance field, starting from introducing maintenance management information systems that are simply software that centralize maintenance information and facilitates the processes of maintenance operations. Simply, it is useful to optimize the utilization and availability of physical equipments. And then we will also focus on the most innovative maintenance policies, like the CBM, the condition-based maintenance, the predictive maintenance, and we will see some techniques to perform, to reach these policies. I think in the last part we will also see some maintenance performance measures. And I think we will have some exercise during the whole course. Sometime I will use my brand new electronic board also today, and we can. I would like that you would participate in these lectures. We are very few people, so sometime I will ask you for some questions, and maybe you can participate. Very simple questions, so don't worry. But as I was saying, I think we will have also some exercise during the whole course. That is of 30 hours for my part. So we can start with introducing the maintenance. I think you all know what maintenance is, but according to its definition given by the British Standard Glossary of Terms, it can be defined as the combination of all technical and administrative actions, including supervision actions, intended to retain an item in or restore it to a state in which it can perform a required function. Now, note that as we will see also in the following, each equipment, each machine, each item, when it is designed to work under specified working conditions related to, for example, humidity, temperatures, loads, and so on. So when we say that an equipment or a system has to fulfill its required function, we mean that it has to work in its standard condition of temperature, humidity, or loads that are given by the designers, by the companies who designed the system. Now, maintenance activities, as you can simply understand, can be either repair or replacement activities, according to the fact that an item, a system, is repairable or non-repairable. Some systems are not repairable, so they must be replaced. Other systems can be considered as repairable, so also simply repair actions can be performed on it. And these activities are necessary for an item to reach an acceptable productivity condition. What does it mean that an acceptable productivity condition has to be reached? It means that an item, a system, can also work not giving the 100% of its potentiality, of its potential. For example, we can decide to leave a machine work to the 70% of its potential, but once defined a threshold, let me say, from the companies. For example, a company decide that the machine that it is acceptable to leave a machine work to the 70% of its potential. Once defined that threshold, maintenance actions should be provided, should be performed once the productivity, for example, is below that threshold. This is to say that maintenance activities are not always needed when, for example, there is a little problem that limits the productivity, because a company can decide to leave the machine work even to less potential, to a less productivity, for example, in this case. And it obviously depends on the cost to sustain, to perform maintenance. It depends on balancing the cost to sustain, to perform maintenance, and the production loss, for example, that I have by leaving the machine working with a damage, for example. And here we can introduce now the concept of fault, that represents the passage of an item from a state in which it is able to correctly perform its function to a state of damage or failure, in which the item is not still able to correctly perform its function, what I was saying before. It is not an on-off system, for example, but there are also intermediate functions, levels for each machines. Which are the most common fault causes? We will refer in the future to fault and failures as synonyms. So if I say failure or damage or fault, we will define, you will understand that they are synonyms for me. Which are the most common fault causes? For example, stresses, impacts, fatigue. In fact, depending on the loading condition and material response, the structural characteristic of the components play a very important role. So, for example, a damage can occur if a component is subject to fatigue. I think you all should know what fatigue is. If you have some doubts or you can't understand me in some concepts, please tell me and I will try to explain again in English. If you cannot still understand, I can also switch to Italian. Unfortunately, I cannot switch. I think Sebastian is from Colombia, is it right? So I cannot switch to Colombian, but to Italian, yes. So stresses, impacts, and fatigue are some of the most common fault causes, but also, for example, temperature is a very important parameter because it mainly affects the specific characteristic of the materials and the spatial and temporal distribution of its sources. Wear out, as we will see when we will talk about the Bethab curve, wear out is a very common state in which components goes after a certain period of their life, and it is due to some normal degradation factor such as friction, wear, and tear. Another important fault cause is the corrosion that mainly depends on the characteristics of the environment in which the component operates, and it generates physical and chemical degradation that could lead to the failure of the system. Another important feature related to maintenance aspects is the maintainability of a system or an item, which is defined as the measure of the ability of an item to be retained in or restored to a specific condition when maintenance is performed. Be careful by personnel having specified skill levels and using described procedures. So maintainability obviously depends on the product design and the technical level of repair of the personnel from the repair process, the procedures, and so on. It is also a characteristic, so not only depending from the component, from the system, but also depending on the skills of the personnel and on the procedures developed by the maintenance personnel. It is a very important factor because it allows to understand how much can be difficult to maintain an item, to maintain a system. So it is important to improve the maintainability of systems in order to reduce the costs of maintenance in general. How can we improve the maintainability of a system? Here, for example, in this figure, you can see that maintainability can be improved by, for example, reducing in a new item, reducing maintenance parts, so old parts, by simply replacing and not repairing systems. That is easier, obviously. Easier access to maintenance. For maintenance, many systems are very complex. For example, if you have to repair the friction of your car, I don't know if friction is the right word. Ok, la frizione essenzialmente, ragazzi. Sorry to Sebastian. It is very difficult because a mechanic has to disassemble several parts before arrive to that one. So making accessible some parts is very important to improve maintainability of systems. This is also related, obviously, to the design of the system. For example, last years is arising the concept of remanufacturing that can be a very important a very important feature to reach, for example, climate neutrality or zero emissions and so on. One of the main problems of remanufacturing a product is the disassembly, and one of the main problem of maintenance is the to arrive to specific failed parts. So providing, for example, design for remanufacturing, design for disassembly will also facilitate maintenance operations. So you can see that a company should start to think about maintenance already during the design phase, but still today many companies don't do this. Okay, now we can define different levels of maintenance, because as you can imagine, not all the maintenance operations led to a similar status after maintenance of the equipment. We talk about perfect repair or perfect maintenance when a maintenance action restores the system's operating condition to as good as new. What means this? Upon perfect maintenance, a system has the same lifetime distribution and failure rate function. We will define later the failure rate function as a brand new one, as a brand new system. For example, the complete overhaul of an engine with a broken connecting rod is an example of a perfect repair. Generally, when we replace an item or an equipment, we are performing a perfect maintenance, a perfect repair. As opposite to the perfect repair, to perfect maintenance, there is the minimal repair or minimal maintenance. That is a maintenance action which restores the system to the failure rate it had when it failed. So in this case, the system is referred to as bad as old. For example, if in your car change tires, the flat tires, you are restoring, the failure rate of the car remains the same, because you are simply acting on a single part of the entire equipment, of the entire system that is the car. So its failure rate, the failure rate of the car is unchanged. We talk about imperfect maintenance or imperfect repair or imperfect maintenance when we talk of a maintenance action that does not make a system like as good as new, but younger. So we are in this case in an intermediate state between the perfect maintenance and the minimal repair, because I cannot achieve a perfect maintenance, but the system is better than of a minimal repair action. In fact, imperfect repair restores the system operating status somewhere between as good as new and as bad as old. So clear imperfect maintenance include these two extreme cases, minimal and perfect repair. For example, engine tune-up is an example of imperfect maintenance because it restores the engine not in a state as good as new, but improves its performances with respect to before maintenance actions. We can also define worse repair or maintenance as a maintenance action which makes the system failure rate or actual age increase, but the system does not break down, or worst repair or maintenance, which is a maintenance action which undeliberately makes the system fail or break down. So worse and worst repair. It is better to not perform maintenance if the result is a worse or a worst repair. which is the main causes of worse and worst repair. For example, repair of wrong part. This is a common problem, for example, when a corrective maintenance policy is performed, is applied. Then in few slides we will see what corrective maintenance is, but you can already understand that a corrective policy is when the company waits until the failure of the system or the equipment to replace the equipment. The problem is that if you have some complex systems, you should identify the failed part. And in complex system, you can arrive to have thousands of parts. So it is not very uncommon that in some cases a repairman, the personnel, can be wrong in deciding which is the part to repair. And in that case, you are if the personnel is wrong on that, they are performing a worse repair, worse maintenance. Other possible causes are to incorrectly assess the conditions of the unit inspected, and this is typical, for example, in preventive policies in which we don't wait for the failure, but we go to inspect the system before it fails. And if the assessment is wrong, you can find that there are no problems on the system, and then after a few days the system fails. In that case, you are performing a worse maintenance, or an unuseful maintenance, if you want, in that case. Other problems can be related to only partially repair a failed part, and not, for example, when the part is not completely replaced, but it is repaired. In some cases, the reparation can be not sufficient and can get worse the situation than the previous one. Other causes of worse maintenance are, for example, repair the failed part but damage adjacent parts. This is also a very common issue. Possible human errors during maintenance activities, or hidden faults not detected during inspections. Now, we talked about some definitions of maintenance, starting from its meaning, looking at maintainability, perfect maintenance, imperfect maintenance, but we still not talk about which are the maintenance objectives, the maintenance goals. Obviously, to perform correct maintenance activities leads to reduce the costs and increase the revenues of a company. So the first reason to perform maintenance activities is for breakdown reduction. What means breakdown reduction? Breakdown reduction means to reduce the time in which, for example, a machine is not working. This leads to maximize the production because, as you know, or as you should know, the overall equipment effectiveness of an industrial plant or also of a machine can be measured or takes into account the availability of the machines. And obviously the availability of the machines is defined as the ratio between the time in which the machine is working and the time and the total time available for production. Reducing breakdowns allows to reduce the time in which machines are not working and allow to increase the availability of machines. If the availability of machines increase, they can produce more. So you can simply understand that maintenance can help in reducing breakdown and consequently in maximizing production. This also concerned the downtimes. The downtimes are strictly related on what we will define later, the mean time to repair, because in general, reducing the mean time to repair allows to reduce the personnel cost of maintenance and allows also to reduce the loss of production, and also in this case to maximize the production, because less time I need to repair my equipment, more time I can produce with my machine. This also another objective of the maintenance is the minimization of energy usage. Why? Because, for example, a failed machine or a machine that has a damage but is still continuing to work can absorb much energy than an optimized, maintained machine, than a machine that is working in its optimal conditions. Then we also need to improve the assets in efficiency, and maintenance can help in this by optimizing assets life. And on this aspect, we will focus in next lessons, next lectures, when we also will talk about the different maintenance policies, such as the condition-based maintenance or the predictive maintenance, whose main objective is optimizing the asset's life, trying to predict the failures, and so leaving the machine working until few moments before failures. Another very important factor for which maintenance is needed is for guaranteeing people's safety and avoiding injuries in workplaces, because remember that many industrial plants can be a little bit dangerous. For example, think to a nuclear plant in which maintenance actions are not performed correctly. In that case, you are mining the people's safety is not guaranteed. Think, for example, to Chernobyl. Or for the ones of you that are mechanical, think about a foundry. If correct maintenance actions related to the furnace are not performed, all the foundry environment can become very dangerous. So these are the main objectives for which maintenance actions are generally performed. Now we can define, we can go towards the definition of the principal maintenance policies. But before of that, we should define two types of maintenance, because each maintenance policy, each maintenance action can be categorized in an ordinary or extraordinary maintenance, which are that. Ordinary maintenance concerns all the operations that must be done to guarantee the correct functions of an asset, and it is categorized as an exercise cost. So when I perform an ordinary maintenance action, I have to pay that action. It is an exercise cost for the industrial plant. In fact, the costs related to ordinary maintenance are expensed immediately and they are not capitalized. For example, substituting the flat tires of your car is an ordinary maintenance action. Extraordinary maintenance actions instead are related to maintenance activities aimed at extending the useful life of an asset. So aimed to increase the book value of an asset. And this type of maintenance activity have to be capitalized because they increase the value of the entire system. So each maintenance action can be classified within these two types of maintenance, ordinary or extraordinary maintenance. Which are the most common maintenance policies? In this slide, they are represented. As you can see, there are two main groups of maintenance policies: the corrective policy and the preventive policy. As I said before, corrective maintenance is performed. It is also called the failure-based maintenance. And it is performed when a system fails, when an equipment fails, when an item fails. So, according to these policies, companies wait for the failure, the damage of a system. Note that corrective maintenance actions can be performed even if the system is still working. When I say something about damage, as I said before, I am meaning something that can reduce, for example, the productivity of a system, reducing its potential. For example, it is not working to the 100% potential, but it is working at the 70% potential, as I said in the beginning of this lesson. Corrective action should be performed when the company understands that it is convenient. Why? Think to a simple example. Imagine that a machine that is working at 100% of its potential during the working shift is damaged, and it is able to perform the 80% of its potential. What does the company should do? In which sense? Is it more convenient to stop the production and repair the machine to restore it and to work to 100% of its potential? Or is it more convenient to wait until the end of the shift, for example, and at the end of the work shift repair the asset for letting it work at 100% on the day before? It is not very simple to understand, because the costs of the two opportunities, of the two alternatives, should be evaluated. Leaving the asset, the machine, working with a reduced potential, as we said, will generate loss of production, because I will not be able to produce what I need. But on the other end, to stop the system, the production system for performing maintenance action during the working shift will completely lead to zero my production. So you should ask, a company should ask if it is more convenient, which one of the alternative is more convenient for corrective maintenance. But note that in both these examples, a damage occurred. So corrective maintenance is referred to something in which the companies wait until the damage occurs, and it is exactly the opposite of the preventive policy, in which companies don't wait for the damage, but they try to anticipate, to predict, in some cases, some damage, or to replace or repair some components before they fails. Why to choose a preventive policy or a corrective policy? Generally, corrective policies are applied when we are dealing with not very much expensive components, or when the loss of productions are not very high. If, for example, the loss of production can be very high, or the components are very important and critical for the entire system, a preventive policy should be better than a corrective one. Now, corrective maintenance can be divided into two main sectors: urgency and programmed, and that was that they are referred to the example I was making before. Urgency is when I have to act during, for example, the work shift, stopping the production. A programmed corrective maintenance can be performed if when I wait, for example, the end of the work shift to perform the maintenance action. For example, I worked before starting my PhD period. I worked for a 1 year period in a maintenance company, and they performed maintenance for fuel distribution plants of Q8. They always performed corrective maintenance actions because the policy adopted by the Q8 was to perform corrective based actions. But in some cases, they and for the most important components, they should perform preventive actions, because for the most important plants, for example, the ones in which the revenues are high, were higher, it was important that the systems, so the fuel distribution plants, can work continuously, because in that case the costs related to the loss of production due to a failure were very high. So for some plants it can be, this is for let you understand that in some cases preventive actions should be preferred to corrective actions and vice versa, according to the costs related to maintenance. Returning to the preventive maintenance policies, you can see that the most important type of maintenance policies are the time-based maintenance, the condition-based maintenance, and the predictive or prognostic maintenance. The time-based maintenance should be also divided in constant interval and age-based. The time-based maintenance is the type of policy in which the maintenance actions are performed after a certain period. So, for example, once a year, I perform the inspection of my system on a predefined day, and it is defined as a constant interval. In other case, according to the age of my system, of my equipment, I can decide to intensify, for example, preventive actions. So, for example, the inspection of the system. Condition-based maintenance and predictive maintenance, on them we will focus in the next lecture. But you can start to know that condition-based maintenance tries to assess the current condition of a system, of an asset, of an item, compares the condition of the item with predefined thresholds, and if some condition exceeds the danger thresholds, the maintenance actions are performed. Predictive maintenance, or prognostic maintenance instead, is a type of maintenance in which, as I said, tries to predict the fault, the damage, simply by estimating the remaining useful life of an item. So, for example, it is like today I say, basing on data retrieved by sensors, on statistical analysis and reliability analysis, it is like I say that my smartphone will live for other 200 days. You can simply understand that it is very, very difficult to predict this type of failure, but if you are able to do that, you can save costs. And so that's why, also thanks to the technologies brought by the fourth industrial revolution that allows to manage a great quantity of data and to integrate that data to make predictions, we can, today, many companies are trying to reach a predictive maintenance policy. Okay. Now, we should also define some important parameters related to maintenance. Let me do this slide, and then we can have a break of 10 minutes. Okay, we need to define, first of all, the mean time between failures. What is the mean time between failures? As the name says, it represents the mean time between two consecutive failures on the same type of system, on the same system or component, assuming that the system or component is repairable. Be careful in the difference between the mean time between failures and the mean time to failure, because obviously mean time between failure is referred to repairable systems. the mean time to failure is referred to non-repairable system. In fact, it represents the mean time of non-repairable system to arrive to failure and to be replaced. The mean time between failure, as you can understand, refers to something that is failed, but the policy, as we said, in which something fails is the corrective, in which we wait that something fails is the corrective policy. So when we talk about instead, for example, a preventive maintenance policy, we should talk about mean time between maintenance. That represents the mean time between two consecutive maintenances on the same system or components. The mean time to repair instead, as I defined before, represents the mean active times needed to complete a maintenance activity. Okay, before start this new slide, I think we can have a 10 minutes break if you agree. Guys, is it okay?
Yes, thank you.
Thank you.
Yes, it is okay.
See you in 10 minutes.
Okay.
Okay, guys, are you there? Can we restart?
Yes.
Yes.
Perfect. Okay. I never ended to share my screen. Okay. Okay. Can you see the full screen now?
Yes.
Perfect. Okay. So we were talking about the definition of some important parameters for maintenance, in particular the mean time between failures, the mean time between maintenances, the mean time to failure, and the mean time to repair. Now, according to these definitions, we can try to estimate, or we can try to evaluate how the mean time to repair is composed, referring to the corrective maintenance policy, to a corrective maintenance policy, and to a preventive maintenance policy. So let's suppose, for example, that we have a component that starts to work at time 0, and it works for a time equal to the mean time between failure, to the MTBF. When the damage occurs, when the failure occurs, a maintenance action has to be performed, and it requires the mean time to repair. Now we can say that when we are performing a corrective action, the mean time to repair is the sum of 4 values. In particular, they are the diagnosis time, the activation time, the repair time, and the restore time. What they are? The diagnosis time is simply the time needed to the personnel for identifying the part of the system that is failed. Often, as we were saying, we have very complex systems made by hundreds of parts. So it is not simple to evaluate which component has failed. This requires a diagnosis time, that is consequently the time in which we are waiting for the diagnosis made by the personnel, by the skilled personnel that perform maintenance activities. The activation time is often not dependent from by the company and by the personnel, because it is referred to the time we should know, for example, to obtain the component from a provider, from a supplier. If, for example, we need a part of a car that has failed, and we need to replace that part of the car, but when we go to buy that part, the supplier has not that part, we should wait the activation time to obtain that component or that part. The repair time, is the time needed to repair the system, so to perform the maintenance activity, and the restore time is the time needed to test if the equipment works, to make the final tests before reintroduce the system, for example, in production. So when we think about corrective maintenance, we should think that the mean time to repair is the sum of these 4 values: the diagnosis time, the activation time, the repair time, and the restore time. Now I have a question for you. if we refer, and maybe you already saw the answer because I let my screen open before, but if we refer to a preventive maintenance policies, how do you think the MTTR, the mean time to repair, is composed? All these times are needed when we consider a preventive policy, or some of them disappear? And if yes, which one and why? Do you have an opinion, an idea? No one of you? Yeah, please. Perfect, perfect.
And
yes,
I
yes.
think also the activation time.
Why?
Because if I think before that I have maybe to repair something, I prepare what I need to do it.
Perfect, you are right. So in fact, if we go to look at what happens when we are performing preventive maintenance, you can see, as your colleagues said, that the diagnosis time and the activation time disappear. That's why, as they correctly said, the diagnosis time in preventive maintenance, when we perform preventive maintenance, no components have failed. So there is no failure. I have not to estimate which components has failed, obviously. But also the activation time disappears, because if I am going to perform a preventive action, I already know on which components I should act. And so I am already prepared for it. So also the activation time disappears. Good. What can we conclude? We can conclude that, obviously, supposing that the repair time and the restore time are the same in the case of corrective maintenance and preventive maintenance. So for example, in the case of preventive maintenance, we are supposing that repair or replacement times are the same of corrective maintenance. We can say that the mean time to repair for preventive maintenance is always less than the mean time to repair for corrective maintenance. Perfect. Now, we can also estimate, for example, the number of hours for maintenance activities, to perform maintenance activities. To do this, we should know some very important parameters that are not very simple to obtain, because we can say that the number of hours for maintenance activities can be seen as the sum of the frequency of occurrence of the height failure, so referred, for example, to the height component, multiplied by the mean time to repair for the height component. By the knowledge of the number of hours, why is it important to know, for example, the number of hours to dedicate to maintenance activities? Because by the knowledge of these parameters, it is possible also to calculate the number of workers to dedicate to maintenance, simply as the ratio between the number of hours and the sum of the diagnosis time, the repair time, and the restore time, all multiplied by eta, that is the rate of absenteeism of the workers. You can see that there is not the activation time in the end work, because it usually does not depend on the workers, but it depends on external factors such as logistics, suppliers, and so on. So you can define in this way, you can define the number of workers to dedicate to maintenance activities. This would be very beautiful if we were able to know accurate information about the FI, that is the frequency of occurrence of the height failure, but obviously it is not fixed, and it is not very simple to evaluate. Like, for example, also the MTBF, or the mean time between failures, or the mean time to failure. They are statistical values evaluated with a certain probability. They are not fixed values. It would be very beautiful, but it is not. So, by means of these equations, you can calculate, for example, the number of workers to dedicate to maintenance. Why is it important, for example, to calculate the number of workers for maintenance activities? Because the general evaluation of costs related to maintenance is a very important issue for companies, because think that in some cases maintenance activities can arrive to represent also the 60% of the total costs of a company. It is a very rare case, but in average we are in I think a percentage more than 15, around 15-20% of the total company costs. The maintenance costs, as all the types of costs, can be divided into two main categories: the direct costs and indirect costs. Which are the direct costs? For example, the cost of workers, the ones we defined before, the cost of materials, because when you need to replace something, you should pay for the new component, but also when you need to repair something, you should use materials. You might use materials for repairs, and eventual external suppliers for maintenance services. Indirect costs instead are referred to the lack of production, the product's quality, reputational damage, or safety conditions for workers. And as you can note from the image in this slide, often the indirect costs are very greater than the direct ones. That's because many companies have indirect costs related also, for example, to reputational damage. That is a very important issue. For example, I can report the example of the company I was working before my PhD period. They worked for Q8. The problem of Q8 was not to pay workers or materials to repair the damaged items. Their problem was the lack of production, but especially the reputational damage, because when a system failed, a person that goes to the fuel distribution plant has not availability of taking diesel oil, essentially. So in that case, there is a lack of production because people, my customers, are not paying for my services, but there is also a reputational damage, because if the first day I go on a Q8 plant and I cannot make diesel oil. The second day I cannot make diesel oil, and so on. At the third 4 days I go from another, but maybe also on the first day I go from a competitor. I go to Esso, for example. Let me say. So there are some costs that are related to reputational damage that for many companies are very important, as well as the lack of production. And this led to, in many cases, to have that the indirect costs are greater than the direct costs. You can see here the evolution of the maintenance costs in relation to the frequency of failures. Of failure. As you can see, in fact, maintenance costs are strictly dependent on the reliability of assets and components, and we will define reliability in few slides. For example, low reliability means high frequency maintenance, while high reliability means low frequency maintenance. And the costs of maintenance policies change according to the frequency of failure of an item. And as you can see, there is an optimal maintenance cost according to the frequency of failure for components. In fact, as you can see, preventive maintenance costs increases for components with low reliability, because in order to avoid failures, companies need to perform more frequent inspections. And this also depends generally on the facts that low reliability elements are used when the indirect costs due to the failures are not very high. So, for example, when you have a component with a low reliability, it is a very cheap component, and in that case, it should not be useful to perform a lot of inspections or for preventive maintenance. When the cost of the item instead is very important, and when we have high reliability components, the cost of corrective maintenance can be very important. When I say the cost of corrective or preventive maintenance, I mean the overall cost. So also the cost due to, for example, the lack of production or the reputational damage and so on. And when you should think that when we have high reliability items, they can be very expensive, and so it is inconvenient to wait until they fail. But it should be useful to apply preventive actions on that type of components. As you can see, you can evaluate the optimal maintenance policy according to the type of components and according to its reliability. Now, what can we do to decrease maintenance costs? Because that's the main issue of many companies when dealing with maintenance problems. For sure, the first thing should be to increase maintenance efficiency, intended as the execution capability that can lead to optimal condition for reducing direct costs. So, increasing maintenance efficiency can help to reduce direct costs. How can I reduce the direct costs? For example, by training maintenance workers to reach an adequate formation. This can help to reduce, for example, the repair time or the diagnosis time. So the train of maintenance personnel can help to reduce the MTTR that obviously represents a cost for a company. We can reduce the direct costs by appropriately managing maintenance jobs, by providing maintenance materials and tools in the right place at the right time, and by respecting the maintenance procedures. All these aspects can help in reducing the direct costs of maintenance that are the ones related to workers, materials, or external suppliers. To reduce the indirect costs of maintenance, I should be able to have prediction capability. In fact, in this case, predictive maintenance is the best policy to reduce indirect costs, because it allows to correctly predict maintenance needs and planning maintenance activities according to the production needs. Another way to reduce costs is to work on the machine availability, on the system availability, or components or items availability. As we defined previously, the availability of a system or a machine can be defined as the total working time, that here I call that time, on the total available time, that is obviously the sum of the uptime and the downtime. As you can see here, you can define the uptime as the mean time between failures, because the time between failures is a time in which the machine is working.